So we were talking about vector fields. This is the definition I had on the board. And we started going through some examples. We said sketching some vector fields. We sketched these two, which were a little simpler. So we had this one, which is a constant vector field. Everything's just moving up. Here, everything's kind of moving on the upper half, everything's moving to the right. On the bottom half, everything's moving to the left. On the x-axis, nothing's moving at all. And then the higher, the further away you get from the x-axis, the stronger it is. So one of the kind of physical ideas I wanted to get into your head is you can think of these as like the flow of some kind of fluid. So I mentioned wind last time. That's kind of the flow of air, which is a gas, which is fluid. But you can also think liquid, so like a river flowing in two-dimensional or even three-dimensional space. And some of the ideas we're going to talk about in the next section really deal with that physical interpretation. And you should kind of have that in your head, that this is something physical that's happening in space. Okay. Lastly, the next example we saw in lecture last week was this, which was this which looks like it doesn't do anything, but then when you actually go to graph it, you realize that it's kind of going away from the origin. And as you get further out from the origin, it gets stronger and stronger. So again, if you're thinking of this as a current, then if you're standing right at the origin, it's not doing anything to you. But then if you step a little bit in any direction, it's just going to pull you in that direction, because that's because it's always going out away from the origin. Okay. Then someone asked, what happens if we switch the x and y coordinates? And we got this funky looking one that was hard to draw, and we couldn't. It was getting kind of messy. But then I challenged you to see, okay, what happens if I throw a negative sign here? If I throw a negative sign here, what does that look like? And I hope some of you took that and kind of worked with it and to see what that vector field looks like. But I graphed it here for you all. So this one I kind of did. I prepped ahead of time, so did some TV magic there. If you throw a negative sign in front of that first one, it suddenly completely changes this picture. So we get, right, we get these kind of circles going around. I drew it a little weird here, so it almost looks like a spiral, but it's not a spiral. You have these, like you go around this circle, and then you go around this circle, and then you go around this. Like the circles are kind of completely disconnected from each other. So at the origin, you're safe. Then if you step away from the origin in any direction, it basically sends you perpendicular to that direction, and you just completely go in circles around and just in that same distance from the origin. Okay. And this description of kind of the path you would take if you were in a certain position is something that we're going to talk about more formally in the coming slides. But then you might be looking at this and thinking, okay, I see like an x and a negative x, which seem like sort of linear terms almost. And yet we get these circle things happening. And so the question is, how did we get circles from this formula? Like, where do circles, circles don't seem to appear in this formula at all. And yet, clearly we're seeing that there's something going around in circles here on our picture. And so it's like, okay, where are the circles coming from? And I'll answer that question later in this section once we start talking about certain things. To get there, first of all, we have to talk about the gradient vector field. So we've been talking about the gradient all quarter. So we've been talking about how the gradient of a function is just this vector, but really it's a vector field because I can plug in points into the gradient to a function, right? So if I take the gradient of a function, I might still have x's and y's, or however many whatever variables I started with, they might still be in the gradient because I'm just taking derivatives. And so I get this gradient vector field. So let's see, I think the best way to explain why I get a vector field is because if I can just do an example here. So if I take the gradient of f here, I think it's going to be one we've already seen. If I take the derivative of this with respect to x, I get y, and with respect to y, I get x, which is definitely a vector field we've seen already. And in fact, it's one of the uglier ones we saw, right? So it was something like, it had these sort of things going on the diagonals. it almost looked like that sort of the one that radiates out, but only on the diagonals, or on this main diagonal, and then on this other diagonal, everything was kind of pointed in. And so we had kind of grossness happening here. Again, this was a messy one. We couldn't really clean up. But then like around here, we had things kind of flowing inward, flowing towards this sort of shape. But the idea here is that this is a way for us to cook up vector fields. It's to say, if you want a vector field, start with a scalar valued function. So f, right, has to be a scalar valued function. If you want a vector field on that domain, then what you can do is treat this function or the gradient of this function like a vector field, and you get, in some sense, you're kind of getting some information about this function here. This function is this is kind of plotting the slopes of this graph. So basically, along this axis here, this function is kind of decreasing down, and along this axis here, you get something that's increasing up. It's kind of hard to see that, but I will try to show that. Maybe I'll do another example here with something. Oops, something a little more clear. So let's do another example. So sketch the gradient of f of xy equals 1/2 x squared plus 1/2 y squared. So this is quadratic in x and y. So it should probably, it's going to be some kind of, if you remember the word I used, it's going to be a paraboloid, right? Which is like a parabola, but living in, the graph is going to live in 3 dimensions, right? So it's kind of like some kind of surface living in 3 dimensions, but it kind of, the cross sections will kind of look like parabolas. And so you can kind of get that from this. You can graph it if that helps, but I'm going to say, okay, what does that have to do with the gradient of this guy? So the gradient is going to look familiar if you can kind of see ahead here. We take the gradient of this guy, the derivative of this with respect to x becomes just x, and the derivative with respect to y is just y. And so again, this is a gradient that we've seen sketched before, but I want us to see it in a new light with respect to the gradient of this function. So if I do this, then we're going to see it kind of always, right? This was the vector field that, it was at the origin, it stood perfectly still. And then as you moved further out, this vector field was kind of pointed outwards. And as you move further out, it gets stronger, right? So when I say stronger, I just mean the magnitude of the vectors are longer. Yeah, so if you're thinking of this as a physical thing, like the flow of some fluid, then longer vectors means stronger current, okay? So we have something like this. So let's think about what that means in terms of the graph, right? What happens of the graph of this function at 0, 0? At 0, 0, we have some fancy vocab words that we've learned about last week to describe what's happening at 0, 0. Anyone know what's happening at the origin here? To describe what's happening to this function. If you could think geometrically, you have a parabola. I think I was going like this earlier, but this one would actually be facing upward. What is happening at the origin there? What would you call that? It converges there. I think there's I I get what you're saying. There's a more precise vocab word that we learned or some vocabulary that we learned last week to describe what's happening there. So if I plug in 0, 0, then the gradient, which is just the differential or the total derivative at 0, 0 is 0, 0, right? So if you get the zero matrix at a point, that's what we call a critical point, right? So anywhere that you see on the gradient vector field, anywhere you see a point, that's a critical point of that function, okay? So we got this critical point of this function, and in fact, what this is telling us is that this is actually a minimum, because anywhere we look, anywhere we go, remember the gradient points in the direction of greatest increase. In any direction, we're going to increase here. So if we go out in any direction, it increases in every direction. So that means that we actually have a minimum here. So you can actually think of this as taking that picture of the paraboloid and kind of flattening it and just kind of saying, this is where the minimum is, and then this is how much we're increasing at every point. So it's kind of pointing out in that way. Does that make sense? If you take this picture, this is kind of saying, okay, there's a critical point there because it's the zero vector. Anytime you get the zero vector, that means you're talking about a critical point, and it's growing in every direction away from that. What would it look like if it was decreasing in every direction? Well, the arrows would be pointed inwards. So let me say that. So local min would look like something like what we're seeing here. So in every direction, it's growing out. Now, they don't have to all be the same length for it to be a local min, but they should all be increasing. Okay. And then for a local max, okay, you'd again have a point like this, but it would be increasing towards the point, right? The arrows describe the direction of greatest increase. And so it should be increasing as you get toward the point, because it should increase to the max. Okay. Does that make sense? I think everyone any questions about this, sort of how we can think of the gradient vector field in terms of what that's telling us about the function? It's basically plotting all of the gradients at the same time. Okay, cool. So we drew pictures like similar to this when we were talking about like Lagrange multipliers a little bit, thinking of the vector fields, or thinking of the gradients as if at every point it's kind of telling you what to do. Okay. So we've seen that we can get a vector field from a function. So that's like taking the derivative so we can think of the vector field as a derivative sort of thing. So you have a function, you take its derivative, this thing that you get, remember the gradient is like a derivative, or the total derivative you can think of as the analogy for the single variable derivative. And so you start with a function, you end up with a derivative, which was called a vector field. Now there's a question of, can we go backwards, right? In single variable calculus, you spend a quarter or a semester learning about how to take derivatives. Then you have to spend another semester learning about how to take integrals, which is going the opposite direction. And so the question becomes a question of, can we actually figure out can we go backwards and get a function out of this vector field? And the answer is kind of. Okay. Basically, what we can do is what I've been physically describing to you, which is if I start at a certain point, where will this flow take me? Okay, answering that question I can do. So I can trace paths along a vector field. So basically, if you're imagining this like the flow of water, like this is, I don't know, you're looking at the top down of some kind of somewhere where like water's flowing down right at this point, and then everywhere the water's just flowing outward. If I just drop a little particle or whatever you want to call it at a certain point, where will that particle flow in the water? Okay, and so that's what we call flow lines or integral curves. So we use these two words interchangeably, either a flow line or an integral curve. A flow line should evoke the image of this physical interpretation of a vector field as like the flow of some kind of fluid. So it's this idea of plopping down a particle at a certain point and following the path it takes along this vector field. Okay. Integral curve is thinking of it a little more conceptually, as if, like I said, a vector field is in some sense the derivative of a certain function. Can we go backwards and integrate that and get some kind of curve out? Okay. So I'll fill in the definition here. So the definition here is that, and this will kind of hopefully evoke why we call it a vector field or an integral curve. But basically, the derivative of this path should be equal to remember. So if we have a path, the derivative is a vector, right? It's a vector in whatever dimension C is in. And so that vector should be the same as if I take F and I plug in C of T. Okay. Okay. So C is the integral of F in the sense that the derivative, right? So we say like, a function is F is the derivative of G. Sorry, F is the integral of G if the derivative of G is F, right? That's kind of how we think of integrals and derivatives. So C is the integral of F because when we take the derivative of C, we just get F, right? And this plugging in C of T is just kind of a little technicality. Okay, so let's see. I'm going to draw some pictures to kind of give us an idea of what's going on. So you have some kind of vector field. Okay, imagine it moving kind of like this. Okay, so let's imagine we plop a point down here. Okay, now I take the derivative. If I want this to move along this flow line, then it's going to kind of do something like this or something. Let me try that again, make it a little smoother. Something like that. And it hits, so at these 3 points, this is C of T. And the derivative of these points, right? So the derivative of these points just lines up with that. So, oops. The derivative at this point is exactly the same as the vector field here. Okay. Now notice it's ignoring a big portion of the vector field. That's because if you plop a point down, right? So if you imagine like that point, like you are that point that gets plopped down in this like river that's flowing. Now imagine over like way out over there, there's some weird flowing happening like in a spiral or something. That's not necessarily going to affect me over here unless I'm kind of pointed in that direction. If it kind of points me away from that direction, I might never see any weirdness that's happening off in the distance, right? That's because if I get plopped here, then I'm only affected by the vector there. And so I follow that. And then I kind of just keep following everything that wherever it takes me. And that might mean that I never get affected by these vectors out here. Okay. So if this vector was like pointed way out here, then I wouldn't know because this vector took me this way. Okay. Okay, cool. So let's see some examples of this in action. So realistically, when for this stage in the class or in your mathematical career, the way we're going to bring up these questions is we're going to say, hey, here is a vector field, here is a curve. Is this curve the integral curve to this vector field? Or should I say, is this curve a flow line for this vector field? And that's all we're really going to ask, because actually, if we just give you a vector field and we say, hey, find a flow line for this guy, that's actually turns out to be a relatively difficult question. And you need some knowledge of differential equations to actually be able to figure that out, which is, a whole other class that you'd have to take. They might actually talk a little bit about it in a lower division in differential equations class. So, but I'm not 100% sure. So, for the sake of this class, we just usually ask you, hey, confirm that this satisfies everything this satisfies this equation here that you're seeing here. Okay, so let's see that here. So here we have a function, a curve C of t, and a vector field f here. And so the question is, does this satisfy that equation? So what are we going to need? We're going to need to plug in, or we're going to need to do C prime here, C prime of t. So the derivative of this guy, which is going to be a vector, and that vector is going to be the derivative of this, which is 1 times 2t times the square root of, it should be 1 over the square root of t squared plus 1. So if you take this derivative, that should be t over the square root of t squared plus 1. If you take this derivative, there's a chain rule. So you get a 1/2 out front, but then you also get a 2t from the inside. So the 2's cancel, and you just get t on the front and on top, and the square root of this on the bottom. As always, if you're not seeing that, just write it down and then check my work after class, or do it on a piece of scratch paper. Show some more steps for yourself so that you can verify that that's true. Okay, so ultimately what we're trying to show is that the derivative of C is equal to the vector field with C plugged in. So that's the left-hand side. Let's check the right-hand side. So f of C of t is just say, hey, look, here we have an x, y, and z. Plug that in here for x, y, and z. So this vector field in the first position is always going to be 1. Your I coordinate is going to be 1 no matter what. And then you get 2 times x. What's our x coordinate? Well, that's just t, so 2t. So far, it's looking really good. Now, what about our third coordinate? Well, in the third coordinate, we get t over whatever z is. Z is the square root of t squared plus 1. Hey, we get exactly what we wanted. So we get exactly what we wanted. So since these are equal, then that shows that this is in fact the flow line for this vector field. Okay, cool. So now notice this is a 3-dimensional problem. So drawing this picture would be a nightmare, because while you could draw, or you could conceptually visualize a 3-dimensional vector field, drawing one on paper would be very difficult. As you saw, drawing the 2-dimensional ones can already get pretty tricky. Drawing the 3-dimensional ones combines all the difficulties of drawing vector fields with all the difficulties of drawing in 3 dimensions. And so it's just pretty difficult. Now, there are tools online so you could visualize them, so like graphing things, but you have to, like I said, mentioned before, Desmos, GeoGebra, those don't do that out of the box. They don't have just type in a vector field and it'll graph it by itself. You have to kind of search like GeoGebra vector fields or something like that, and then some people online have already made kind of tools on top of GeoGebra to kind of help you with that. But yeah, so visualizing these can be kind of difficult, but okay, cool. Any questions? Yeah, so showing that something is a flow line, not too hard. You just plug in, You just take the derivative of the line of the curve, and then make sure that it equals the vector field with this XYZ plugged in. Okay. So let's see this next one. Okay, so now we're going to see this curve here, and we're going to see, is this the integral curve of this vector field here, which is a vector field we've seen before, and I'll talk about that in a second before we wrap up this section. Okay, so as I said, we start by taking the derivative of t, and then we take, so that's going to be negative sine of t, and then cosine of t. And then if I take f of c of t, well, then I take this, I plug in here. Sorry, that is x, so that's my x and my y. So then I plug them in here, get negative sine of t, cosine of t. And there you go. Okay, so let's talk about this problem specific. So that, again, you're done here. You saw that these were equal. It's all good. But let's talk a little bit about this, because this vector field is one we saw before, right? It's the one that I was saying, it feels kind of weird because there's nothing circular about this, right? It doesn't feel like a circle because it's like just linear terms. And yet somehow when we graphed this vector field, you get something like this. You get kind of these circles of increasing radius, and that seems to be what the vector field is telling you. And the question is, how does that happen? How do we get circles out of this here? And it turns out that the reason we get circles out of this is because the derivative of cosine is negative sine, and the derivative of sine is positive cosine. And so because that picks up a negative, because the derivative of this is just the negative sine of, is just the negative of this. So the derivative of your x coordinate is just the negative of your y coordinate, and the derivative of your y coordinate is your x coordinate. That means that this negative y comma x is just going to be the derivative of this curve here. Okay, and notice that this here is the curve of radius of the circle of radius 1, right? This here is just this circle here, which does exactly these curves, these flow lines are exactly like what happens when you plop in a point anywhere here. It just kind of goes around in this circle here, like we see here. Okay, cool. Any questions? And we could have put any coefficients here. We could have put like 2 cosine of t and 2 sine of t, and we just pick up some negatives. And that's just telling us that we have, like I said, we can have multiple different flow lines for the same vector field. So I could have, if I plopped down my point over here, it would have gone in a bigger circle. I plopped down my point out here, it would have gone in a bigger circle. I could have plopped down 0, right? If I put 0, 0, then I could have just 0, 0, the derivative is still 0, 0, which is equal to negative 0, comma 0. So that would have stayed just right at the origin the whole time. Okay, cool. Any questions on that? So the derivative of that function n times will always be a circle. Should be careful with that. So that is saying something slightly different. So in this case, if you like graphed this as like a curve, you wouldn't necessarily get a circle. I think you do. Yeah, of course. Yeah, you're still going to get a circle because of the Pythagorean identity. You'll still get a circle, but that's not, you're thinking of these now as the arrow, the vector field here. So it's like this vector field of arrows here. Okay. But yeah, you are right that the derivative of of this function, if I keep taking the derivative, you will still get a circle. But the way it relates to this vector field is the fact that the vector field is kind of pointing in a certain direction. Okay, cool. So yeah, if we want to show that a curve is not the flow line or the integral curve for a vector field, then we just need to, we do the same process, but we just want one of the, we only need one of them to be not equal, okay? So if it's not an integral curve, would mean at least one coordinate is not equal. Okay. Good question. Okay. Cool. Any other questions? How am I doing on time? Let's see. So we're going to jump into section 4.4 here. With divergence and curl. So that's what we're going to talk about in this section. So as we enter this section, it's important to reiterate something that I was mentioning in the last section, which is that we should have this idea of vector fields as some kind of physical interpretation. So we're thinking of them, thinking of a vector field as literally the flow of some kind of fluid in space, either on the two-dimensional plane, so some kind of two-dimensional fluid, which sounds silly, but with vector fields, you can actually talk about that, and then, or like in three-dimensional space. So one of these things, the divergence, is a general sort of thing that we can talk about, but the curl specifically is something that is unique to the to two dimensions. Okay. So, and I'll talk about those physical interpretations in just when we start covering these a little more deeply. So let's start with this divergence idea. So you're given a vector field. So like I said, it can be in any dimension. So remember, a vector field is just a function which takes in a point in n-dimensional space and spits out a vector in n-dimensional space. So it's just a function from Rn to Rn, but you're thinking of the input as a point in Rn and the output as a vector based at that point, okay? At that point you inputted, okay? So that's how we get those drawings of, right, at a certain point, the vector field gives you a vector at that point, okay? So this is what it's gonna look like. And now I left it off, but each of this, like this is a function in n variables. So each of these is a function in n variables, right? And so the divergence here is just going to be the gradient as an operator dot product f. Okay, so this is a vector. The gradient as an operator, we're thinking of the gradient as just the operator d dx1, d dx2, all the way up to d dxn, right? So this is just the operator, right? This is not, we don't have an actual function that we're taking the derivative of. This is just the operator, which is saying, hey, take the derivative of a function in the first variable, the second variable, et cetera, et cetera. Okay, so if I take the dot product of these two, basically what that means is we're going to take a sum from, I can write it in some notation, but I think I'll write it just a little more explicitly using this here. So this is, I take this this partial derivative of this function here, right? So I'm basically going to take the first coordinate with the first coordinate, then the second coordinate with the second coordinate, and then add all of those together, right? So df1 dx1 plus df2 dx2 plus df3 dx3, etc., dfn to dxn. And that there's our definition. So you just take the partials of each. So like you're going to have, a bunch of coordinates, and you're just going to take the the derivative of the first coordinate with respect to the first variable, second coordinate with the second variable, et cetera, et cetera. Okay, so if you're thinking of this in 3 dimensions, right, then you just have df1, dx, df2, dy, and df3, dz, right? So you just take it derivative of the first coordinate with respect to x, then with respect to y, then with respect to z of each of the coordinates, okay? So this seems like, okay, I just like put together a bunch of formulas that I can already take. Like I already know, I know what dot products are, so I can just take this. I know what the gradient is. I can just take this sort of, just take the derivatives of this guy and then the derivatives of this guy, and then add all that together. It was like kind of just randomly put these things together. So the question is, how does this? What is the physical interpretation of what's going on here, so that we can have some intuition of why we're doing this? So the physical interpretation of this is that what this is actually telling us is how much this vector field is either expanding or compressing. So this tells us, so the divergence tells us how much a vector field is expanding or compressing. Okay. Okay. So now I'll notice that each of these, when I take the derivative, I might still have variables in this. So this ultimately is going to be a number, a scalar, but in terms of my variables x1 through xn. So we'll see that here. So let's start with this. The first few examples aren't necessarily going to show that off very well, but let's start with, we'll do one example at a time. So if I take the divergence of f here of this first one, the divergence of f is going to be d dx of x, and then d dy of y. So in this case, you just get 1 plus 1, which is 2. Okay. So remember, this vector field, you should have a picture of it in your head now, because we saw it a few times in the last section, is just increasing in every, it's just like going out in every direction, right? So it's just kind of, it's just radiating out from the origin. So this number is greater than 0. So that means that tells us it's maybe I'll do that in a different color. So because this is greater than 0, so that means that f is expanding. So divergence, you should think it's diverging away. So if I put 2 points, relatively close together, if I dropped 2 particles relatively close together, they would get further apart because they're just expanding. So they're diverging from each other. So it's expanding. Okay. Now let's see this next example. Oops. Okay, the derivative. So the divergence of negative x, negative y. So it's d dx negative x, d dy of negative y. So this is going to be -2, right? Because I get -1 plus -1, so I get -2. So it's similar, but in the opposite direction. So I get a negative. So this is, instead of expanding, this is compressing. So the picture of this is similar to the picture of the first vector field we saw, except everything is kind of going, the arrows are all pointing inward toward the origin. So that's, if I put any 2 particles anywhere, they would eventually all lead to the origin. They'd all get me to the origin. Okay. So you actually go from expanding to compressing. Now notice for both of these examples, I just got numbers, and for this third example, I'll also get a number. But technically, just by taking derivatives, I might not get rid of my variables. So there might still be variables. So it might be, what that means is that it might be expanding in some places and compressing in other places. Okay, so I might have some like kind of expansion out here and then compression out here, in here, over here, okay? Cool. So let's do, on this page, we'll probably only be able to fit one last example. And then we'll do this, number 4, we'll do that on a separate page. Okay, start with number 3 here. Taking the divergence, again, take the derivative with respect to x of negative y, and the derivative with respect to y of positive x. Right, this is that vector field. Hopefully it looks familiar at this point. This is the one that went around in circles, right? So the negative y comes from the fact that the derivative of cosine is negative sine, and then the positive x is the derivative of sine is positive cosine, right? So you're going around in this circle counterclockwise, okay? So what do you get here? You get 0 plus 0, so you get 0. Does that make sense with what we're saying? Right, if we're going around in circles, you're not going to be compressing or expanding. You're just kind of, everything's just kind of staying the same distance. So if I put two particles relatively near each other, then they're both just going to go around in circles, and they're going to kind of stay near each other. Okay, so they're not going to get farther apart. They're not going to diverge. They're not going to converge. They're just going to kind of chill, keep going around their respective circles. Okay, and so this last one is not compressing or expanding. And now notice that doesn't mean it's not moving, right? It's still moving, still going in the circular motion. It's just not expanding or compressing, right? It's just kind of chilling, going in circles. There are other ways to get 0 as well. But yeah. One last example here. So this one's in 3 dimensions, a little harder to draw. You have x squared plus y squared plus z squared. Okay. So if I compute this, the divergence of this one is harder to draw, but might help if you look at, as a smaller example that's similar to this, looking at fxy equals x squared y squared. So this one in 2 dimensions. If you have some tool that's helping you visualize these vector fields, looking at this one will give you a similar picture to looking at this one. But you get the divergence of f is the partial of x, the partial with respect to x of x squared, plus the partial with respect to y of y squared, plus the partial with respect to z of z squared. So you get 2x plus 2z, or 2y plus 2z. Okay. So now we can't really say whether this is always positive or always negative, right? In fact, sometimes this is going to be 0 if I choose the right number. So for example, at the origin, this is 0. So at the origin, if I put that point down, it's not going to go anywhere. And now it kind of depends on where what I plug in for x, y, and z. So this is, sometimes it's compressing. Sometimes expanding, and sometimes neither, right? Because you can get 0 for a lot of you can think of plenty of examples where you get 0 here. And in fact, if you think about the graph here, basically what's happening here is if I set this equal to 0, that's a plane, right? 2x plus 2y plus 2z equals 0 is a plane It goes through the origin, and the direction in the normal vector is 2, 2, 2, 2, 2, 2, 2. And so you get this plane in three-dimensional space where the vector field is just kind of, it's not expanding, it's not compressing, it's just kind of chilling, right? And so there it's not expanding or compressing. And then, yeah, so can I show this graphically? I can try. Let's see if let me pull up GeoGebra. I can't graph the vector field, but I can show you kind of what's happening. So where did, oh, there it is. Okay. Okay. Okay, let me switch to this GeoGebra here. So let me switch that out. Okay, cool. So if I set 2x plus 2y plus 2z equals 0, then you get this plane here in three-dimensional space. So what is happening here is that at this plane, on this plane, the vector field is not expanding or compressing. But if I look over here on one side of the plane, so let me stop the spinning here for just a second. If I look on one side of the plane up here, in fact, then no matter what I do, I'm going to get a positive output. So I don't know if this lets me, I don't know if this lets me do inequalities. It might be kind of hard to see if I do greater than 0. Yeah, it can't really draw that on the graph. Yeah, that's not it would just be like all of this space up here. So if I kind of went at that perfect angle again. Yeah, so if I over everything over here, you can't really see it, so there's no use having that. But everything over here would give me positive, meaning out here it's expanding, but down here I'd get something negative. So over here it's compressing. This line is kind of acting like this plane is acting like a wall between the stuff that's expanding and the stuff that's compressing. Okay, does that make sense? Okay, cool. So let me switch back to this. Okay. Yeah. So that plane is kind of acting like this, the wall that separates the stuff that's expanding and the stuff that's compressing. So one thing that I want to add here, is just a little note that, like a vocab note. The divergence of a vector field is an example of something called a scalar field. Which is it's what it sounds like, but I'll give you more than that. So we talked about a vector field, which is at every point you get a vector at that point. Which, but the scalar field is at every point you get a scalar. Which is just a number. So you could think of this as kind of telling you, okay, so I have this vector, the divergence, which is you get, you have this vector field, which at every point is giving you a vector. And then somehow from all of that, you get at every point, instead of just getting a vector, you get a number. There are other examples of scalar fields. For example, if I just took the magnitude of that vector, that would be a scalar field, because at that point I now get a scalar. But this scalar field relates to kind of the behavior of that vector field, kind of at a slightly bigger scale. Okay, and so here we get an example of a scalar field. It just means because f, right, is a function from Rn to Rn. The divergence of f is still a function in n variables, but now instead of giving you a point, it gives you instead of giving you a vector, it gives you a number. So let me spell that out a little bit. So the inputs, points, and the outputs are vectors. That's what a vector field is. Then when you take the divergence, the inputs are still points, but now the outputs are numbers or scalars. In this case, in the case of a scalar field is a more general idea. It's just at every point you have some number assigned to it, and then what that number means can vary. But for the divergence, specifically for the divergence, that number at any given point is telling you at this point, is it expanding or compressing, and by how much, right? So that's kind of what this is telling you here. Okay, cool. So the divergence is a scalar field. Okay. At every point, you get a number, a scalar, which tells you how much it's compressing or expanding. Okay. Let's look at the next topic, which is something called the curl. Okay. And the curl is different from the divergence in a big way, because the vector field has to be in 3 dimensions. Okay. We'll talk a little bit about, you can do some tricks to get something that's kind of like the curl in 2 dimensions, but really the curl itself gives you has to be in 3 dimensions. So the reason it has to be in 3 dimensions is because the definition of the curl is given by a cross product, and we saw that cross products have to be in 3 dimensions. So if you do this, the derivative of f, so f is equal to, let's say, f1, f2, f3. Then this curl has to be the cross product of this with the gradient. So we write that as I, j, k, and then we do ddx, ddy, ddz, and f1, f2, f3. And so we get, when we actually compute this, you get the derivative of y, so the derivative of f3 with respect to y minus the derivative of f2 with respect to z. That's the ith coordinate. The derivative of f, so I'm going to do the minus sign here, f3 with respect to x minus the derivative of f1 with respect to z. This is times k, or times j, plus the derivative of f2 with respect to x minus the derivative of f1 with respect to y, k. Okay, so you use this cross product, which is, remember, it comes from this formal determinant here to give us this. Now, sometimes a note about this is if you can just switch the order of these and this becomes a plus sign. So sometimes it's written that way. So it's df1 dz minus df3 dx with a plus sign there. So we can write it either way. Okay. So now the question becomes, how can we physically interpret this? So let me start by kind of going back to the physical interpretation of what a vector field is. So a vector field, like if we're living in 3 dimensions, is just kind of the flow of some kind of fluid. That's what we want to be thinking about. And what we were talking about when we talked about flow lines earlier today is we said we dropped a particle, which is just like an infinitesimally small little particle into this space and saw how it flowed. Okay, what if we dropped something bigger into this medium? Well, then it would also move, and its center of mass would basically act like the particle, right? It would move along this flow line, right? The center of mass of this guy would move along the flow line. But for example, if in the extreme case, if you have something like long and thin, like a pen here, if I drop this in, if the vector field is stronger over here than it is over here, what's going to happen? So if you're imagining that it's flowing stronger on this end of the pen versus this end of the pen, what's going to happen, right? If this force is stronger than this force is really weak, then what's going to happen here? There's going to be some spin to it, right? I'm going to get some spin to it, okay? And if we imagine something that's a little less, long and skinny like this, have a Rubik's Cube here, right? Then it might move, it might kind of move at an angle, right? It might not spin in just like this. It might the forces might be acting on it in a way that it starts spinning. The point is that if you put a 3-dimensional object into some kind of 3-dimensional vector field, it's gonna start spinning, okay? Unless it's like a perfect vector field that's all moving the same magnitude in the same direction, in which case it's just gonna kind of float like that. But if you put it into some kind of medium where there's some kind of vector field acting with any kind of like nuance, in the sense that like some of the vectors are going to be like longer than other ones, and you put this in, then it's almost certainly going to start spinning, right? But when something spins, it's just spinning in 3 dimensions, it's just spinning along some axis. You can always find some axis, okay? So the output of the curl is a vector. So the direction of the curl of F is the axis of spin on a rigid body. So rigid body is like fancy physics terms that describe like something that's rigid. If it was like something malleable, then like a piece of paper, right? If I put a piece of paper in a medium, it has some give. So it like, if I put too much pressure over here, this side might stay the same, might not move as much. So it's kind of weird. So we want to think specifically if we have something that's rigid, that it's kind of fixed like this. This gives you on a rigid body moving according to F. And so this is a vector, so it has 2 things. It has direction, but it also has magnitude. The magnitude is the speed or velocity of the spin. So I said velocity because if you're talking about spinning, velocity basically, so spinning is one dimensional. All you have is the angle, the rate of change of the angle. But because of velocity can be positive or negative in that sense, right? So you can either spin in this direction or you can spin in that direction. And it's going to basically depend on whether the vector is pointing up or pointing down, right-hand rule stuff, which has to do with the cross product here. So the cross product, you always put the gradient on top. And we saw when we were talking about cross product that if we switch the order of those, you switch the positive and negative. But in this case, it's always going to be in a certain direction. And so whether it's moving clockwise or counterclockwise with respect to that direction, that's going to determine whether you get a positive or negative number. That's more of the minutia of it. So let's just pause for a second. Understand the curl. You have a vector field. The curl is saying, okay, drop something bigger, not just a particle, but something bigger, a rigid body, into that medium that has this vector field acting on it. It's gonna spin, right? Unless there's very particular circumstances that allow it to not spin, right? But it's almost certainly gonna spin. Okay. And so like it might spin kind of weirdly, but no matter how it spins, there's some axis of rotation for that spin. Okay, at any given point. And now that axis might change over time. For example, if it's spinning like this, but then the vector field is causing it to do something like this, and now it's spinning like this, that might, so the axis of rotation may have changed over time. But the point is that at any given point, or it changed as it moved through the medium, at any given point, there's a single axis of rotation. Okay. And so the vector field is giving you that not only the axis of rotation that with the direction, but then the magnitude is telling you how fast it's spinning. Okay. So that's kind of giving you, that's kind of what that's telling you. Okay. Cool. I think I have some examples here that we can do. So let's start by just taking the curl of a couple of vector fields here. And I think this is going to put us at time, and we'll finish up tomorrow with more examples, and then I will do some. Yeah, so I'll finish up a couple of examples, introduce one more thing, a topic about in two-dimensional space, what we can talk about with curl, and then kind of compare and contrast the three concepts we learned in this class. Okay, so let's compute the curl here. So we'll take the curl of f. So you could memorize this formula here. I think it's probably easier to just set up. I mean, if you don't like, I don't like memorizing things, so it's easier to probably just set up this matrix every time and just compute the determinant every time. But you are welcome to figure out what works best for you. And I find that when I if I memorize that formula, then what ends up happening is I just kind of, every time I recall it, I'm just going through this in my head. And so might as well just write it down since we're doing that anyway. Okay, now what we're going to notice about a lot of these is that we're going to get, in this case, so d dy, so d dy of z minus d dz of y, and that's going to be on I, plus d or minus ddx on z minus d dz on x times j, plus ddx on y plus or minus ddy on x times k. Okay. Now, what in this case, these are all zero, right? Because derivative of with respect to y of z is 0, and then so on and so forth. So you just get 0i plus 0j plus 0k. So what this means is this is one of those weird cases where if I dropped a rigid body into the into this vector field, it wouldn't move. It wouldn't spin. That's the important thing. So if I drop my Rubik's cube here into into like a pool that, or some kind of fluid that was moving in this, which remember that's the thing that kind of expands, and it wouldn't spin at all. Okay, and that might seem kind of weird because like, oh, there's definitely a lot of movement here, right? The divergence was huge because it kind of it diverges as you get further from the origin. But no matter where I put this, the forces being applied are going to be kind of the same, kind of all going kind of in the same direction. Like you can get equal you can get equal forces acting on in every way on this guy. So it's just going to kind of move outward away from the origin. Okay, cool. Any questions on that?